So welcome back to this part of this sequential circuits lecture. Today we will start about the counter and we will mainly see the asynchronous counter over here. So what is counter? A digital counter is a set of flip-flop whose states change in response to the pulses applied to it. Okay. So applied to the input of the counter rather. The flip-flops are interconnected such that their combined state at any time is the binary equivalent of the total number of pulses that have occurred up to that time. Thus, as the name implies, a counter is used to count the clock pulses. Alright. A counter can also be used as a frequency divider to obtain the waveforms with frequencies that are specific fractions of the clock frequency. And they are also used to perform the timing function as in digital watches, to create the time delays, to produce non-sequential binary counts, to generate pulse strings, and to act as frequency counters like that. Okay. So you can see over here, this counter will count the clock pulses. Here it is an n-bit counter is shown. So when the clock pulse is active, it will produce the n-bit output. Then again, this is a positive. This will work when the positive edge of the clock pulse here, and this is the negative edge of the clock pulse. So when the negative edge of the clock pulse appear, this counter will generate the n-bit output. Okay, and the counter, it can maybe up counter or down counter. Up counter means it will count in the upward direction, that is 0, 1, 2, 3 up to capital N. Okay. What is a down counter? It is a counter which counts in the downward direction. That is capital N, N minus 1, N minus 2, N minus 3, 1, 0, like that. Okay. Each of the counts of the counter is called the state of the counter. Okay. The number of states through which the counter passes before returning to the starting state is called the modulus of the counter. Hence, the modulus of the counter is equal to the total number of distinct states or counts including 0 that a counter can store. So if we tell it in other words, the number of input pulses that causes the counter to reset to its initial count is called the modulus of the counter. If you have a 2-bit counter, how many states you will have? It will have 4 states. It is called mod 4 counter. It divides the input clock signal frequency by 4. Therefore, it is also called the divide by 4 counter. Alright. It requires 2 flip-flops. Similarly, for a 3-bit counter, okay, how many flip-flops we need? We need 3 flip-flops. Okay. And it will be having 2 to the power 3, that means 8 states. Okay. It divides the input clock frequency by 2 cube, that is 8. In general, if you say an n-bit counter will always have n flip-flops and 2 to the power n states and divides the input frequency by 2 to the power n. Hence, it is a divide by 2 to the power n counter. And a counter, it may have a shortened modulus. Okay, this type of counter doesn't utilize all the possible states. Some of the states may remain unutilized, that is invalid. The number of flip-flops that are required to construct the mod n counter equals to the smallest mod capital N counter, rather I say mod capital N counter, which is equal to the smallest small n, for which capital N less than equals to 2 to the power n. What I mean is capital N less than equals to 2 to the power n. Okay. So a mod capital N counter divides the input frequency by this capital N. Okay. Hence it is called a divide by N counter. Now we will start about different counters. First, let's say what is the difference. Now counters are two types. One is the synchronous and another one is the asynchronous. What is synchronous counter? If we see the difference between asynchronous and synchronous counter, in asynchronous counter, the flip-flops are connected in such a way that the output of the first flip-flop drives the clock for the second flip-flop, and the output of the second clock drives the third, and so on. But in synchronous counter, there is no connection between the output of the first flip-flop and clock input of the next flip-flop, and so on. Okay, because in asynchronous counter all the flip-flops are not clocked simultaneously, whereas in synchronous counter all the flip-flops are clocked simultaneously. In asynchronous counter, design and implementation is very simple, even for more number of states. Whereas in synchronous counters, design and implementation becomes tedious and complex as the number of states increases. The main drawback of this asynchronous counter is the low speed. As the clock is propagated through the number of flip-flops before it reaches to the last flip-flop, because the output of the first flip-flop will drive the clock of the second flip-flop in this case, right? But here in synchronous counter, all the flip-flops are clocked simultaneously. So the total propagation delay is equal to the propagation delay of only one flip-flop. That is why they are faster. Okay, so if we discuss about the 2-bit ripple up counter using the negative age triggered flip-flop. So in this figure, what we are observing? We are observing a 2-bit up counter. In the this counter it will count in the order of 0, 1, 2, 3. Again, because this is 2-bit, right? So after 0, 0, 0, 1, 1, 0, 1, 1, it will again start counting from 0, 0, 0, 1, 1, 0, 1, 1, like that. Okay. So in this figure, you are observing a 2-bit triple up counter using the negative age triggered JK flip-flop. Okay. So, and its timing diagram is also shown over here. So, let's say the counter is initially at 0, 0 state. This is flip-flop 1, this is flip-flop 2. So, let me write, this is my Q1 and this is my Q2. Okay. So, first we are considering the counter is at initially 0, 0 state. Okay. So when you are applying this J and K input, both are tied to 1. So when you are giving the first clock pulse to this first flip-flop, what will happen? When J, K both are 1, when it gets the clock pulse, what will happen? The flip-flop will toggle. This first flip-flop will toggle at the negative edge of the first clock pulse. Okay. So initially both were 0. Now, since the flip-flop toggles, this flip-flop toggles, so this Q1 will become 1. Okay. Now, that means Q1 is going from low to high. Okay. So, this becomes, if Q1 becomes high, so this becomes a positive going signal to at the clock input of this second flip-flop, right? So flip-flop 2 won't be affected, and hence the counter after the 1 clock pulse will be Q1 is 1 and Q2 will be 0. Okay. Next, what will happen? Now, at the negative going edge of the second clock pulse, when again this flip-flop is getting the negative going edge of the clock pulse, what will happen? Then again this flip-flop 1 will toggle. Okay. Again again this flip-flop 1 will toggle. So now Q1 will change from, this Q1 will change from 1 to 0. That means it is changing from high to low. And these, when these negative going pulse, it is when this negative going pulse is applied to the clock of this second flip-flop, it activates this second flip-flop, and hence this Q2, it goes from, now this flip-flop will toggle, this Q2 will go from 0 to 1. Okay, that means from low to high. So that is, now my Q1 is 0 and Q2 is 1. That is 1 0 is the state of the counter after the second clock pulse. Alright. Now at the negative going edge of the third clock pulse, what will happen? Again this first flip-flop will toggle. Okay. Again this first flip-flop will toggle. Now again this Q1 will change its state from 0 to 1. Okay. So these, when this Q1 becomes 1, this becomes a positive going signal to this flip-flop. Okay. So this flip-flop won't be affected. So the change, the output, therefore Q2 will remain 1 1 1. Okay, that is 1 1 is the state of this counter after the third clock pulse. Okay, then again at the negative going edge of the fourth clock pulse, this flip-flop will again toggle and Q1 will go from 1 to 0. Okay, and when we are getting 0 over here, then what will happen? This flip-flop is getting the negative going pulse. Okay, so now this flip-flop will toggle and it will change the state. So Q2 will come from 1 to 0. Okay, so now Q2 and Q1 both are 0. So 0 0 is the state of the counter after the fourth clock pulse. Alright, so for subsequent clock pulses, the counter goes to the same sequence of states. So it acts as a mod 4 counter. Okay, where this Q1 is the LSB and Q2 is the MSB. Okay, how the counter is counting? 0 0 0 1 1 0 1 1 0 0 0 1, etc. Right? Next, this is the timing diagram. Right? This is the timing diagram. So here the flip-flops are responding. This is the negative edge triggered flip-flop, right? That means when the flip-flop is changing its state from high to low, then only the flip-flops will be triggered. So initially both Q1 and Q2 were 0 0. So when the first negative going edge of the clock signal appears over here, what happens? Q1 will, this flip-flop toggles, Q1 will change its state from 0 to 1. How long this 1 will continue? Until the next negative edge of the clock pulse appears over here. At that time, what will happen? Since Q1 over here is 1, so it won't trigger this second flip-flop, right? So Q2 will continue to be 0. Now at the second negative going edge of the clock pulse, what is happening? Now this Q1, it became 1 in the previous state. Now it will again toggle to the 0 state. Now this 0 is coming over here. Now this flip-flop will toggle and it will change its state from 0 to 1. Likewise, it will continue and it will keep on counting from 0 0 0 1 1 0 1 1 like that. Okay. Now we will see the 2-bit triple. Previously we have seen 2-bit triple up counter using the negative edge triggered flip-flop. Now we will see the down counter. So down counter, how it will count? It will count in the order of 0 3 2 1 0 3. That is 0 0 1 1 1 0 0 1 0 0 1 1, like that. Okay. So here what we are observing here you can see these Q1 bar. This Q1 bar of the first flip-flop is connected to the clock of the second flip-flop. Okay. So let initially all the flip-flops are reset. That means the count of all the flip-flops be 0 0. So this is my Q1 and this is my Q2. Okay, so initially both Q1 and Q2 are 0 0. Okay, so at the negative going edge of the first clock pulse, what will happen? This first flip flop will toggle, so Q1 will become 0. Okay, so this Q1 will become 1 because previously it was 0 0, right? So when you are giving the clock pulse, this Q1 will go from 0 to 1. Q1 will go from 0 to 1. So if Q1 is 1, then Q bar will be 0. Okay. So this negative going signal, what will happen? It is going to the clock of this second flip flop. Okay, so this flip flop will toggle, this flip flop will toggle, and this output Q2, it will go from 0 to 1. Okay, so at the negative going, so after the 1 clock pulse, we can say the state of the counter is 1 1. Okay, so at the negative going edge of the second clock pulse, what will happen? This Q1, this flip flop will toggle and Q1 will change its state from 1 to 0. Okay, and Q1 bar will go from 0 to 1. Okay, so that means this flip flop, it is getting a positive going signal and it won't affect this flip flop, and therefore Q2, it will remain at 1. Okay, so the state of the counter after the second clock pulse, we can see it is 1 0. Now at the negative going edge of the third clock pulse, again this first flip flop will toggle, right? So what will happen? This Q1 bar, it will again go from 0 to 1, right? If Q1 bar is going to from 0 to 1, Q1 bar, what will happen? It will go from 1 to 0. So a negative going signal is appearing at the flip flop, the second flip flop. Okay, so it will toggle the second flip flop and Q2 will change its state from 1 to 0, right? So the state of the counter after the third clock pulse is 0 1. Okay, then again at the negative going edge of the fourth clock pulse, what will happen? Again this first flip flop will toggle, Q1 will change its state from 1 to 0 and Q1 bar will be 1, right? Q1 bar will be 1. So this positive going signal Q1 bar doesn't affect the second flip flop and this Q2 will remain at 0. Okay, so hence the state of the counter after the fourth clock pulse is 0 0. So for subsequent clock pulses, the counter goes through the same sequence states and it counts in the order of 0 0, 1 1, 1 0, 0 1, 0 0 again, 1 1, like that. Okay, so this is the timing diagram. First, these flip flops will be triggered at the negative going edge of the clock pulse. So whatever we have discussed over here, initially both Q1 and Q2 was 0. Okay, when the negative going edge of the first flip flop appears, Q1, this first flip flop will toggle. That means it will go from 0 to 1. How long it will stay in the 1? Until the next negative going edge of the clock pulse appears. But when this Q1 is becoming 1, Q1 bar becoming 0. So this flip flop will toggle and it will change its state from 0 to 1. Okay, so again when the Q1 is becoming 1 at the negative going edge of the second flip flop, then at that time Q1 bar is going from 0 to 1. So this flip flop won't toggle, second flip flop won't toggle, and what will happen? It will continue to be in the 1 state until the next negative edge of the clock pulse appears and it will continue. Okay. So have seen 2-bit triple up counter and down counter. Now if we are asked 2-bit triple up down counter, how the operation will look like? So this as a name indicates that it is an up down counter. So the counter, it can count both in upward and downward direction. Okay, so an up down counter, it is also called a forward and backward counter or a bidirectional counter. So you can see a control signal or a mode signal, capital M, is required to choose the direction of the count. When this signal M is 1 for up counting, this Q1 is transmitted to the clock of the second flip-flop, and when M is 0, that means we are applying an inverter over here. For down counting, this Q1 bar is transmitted to the clock of second flip-flop. Okay, so this is achieved by these two AND gates and one OR gate. Okay, and the external clock signal is applied to the first flip-flop. So the clock signal to the second flip-flop will be Q1 into up counter, that means when M is 1, plus Q1 bar into when M is 0 into down, and you are giving these two AND gates output to the OR gate, and this will go as a clock signal to the second flip-flop, that is Q1 M plus Q1 bar M bar. Alright, now if we see, so far we have seen the up down counter utilizing the negative age triggered flip-flop. What if now we are using the positive age triggered flip-flops? Okay, so over here you are observing a 2-bit triple up counter using the positive age trigger. No bubble is there, so it is a positive age trigger flip-flop, and this is the timing diagram. Okay, so the difference is, this is a up counter, so but positive age triggered. So the Q1 bar output of the first flip-flop is connected to the clock of the second flip-flop, and the external clock signal is applied to the first flip-flop. Alright, the first flip-flop toggles at the positive going edge of each clock pulse, and these second flip-flop toggles wherever this Q1 bar, it changes from 0 to 1. Okay, and the state transition occurs at the positive going edge of the clock pulse. The counting sequence we already have seen in up counter 0001, 1011, 0001, like that. Okay, so process is same, only here Q1 bar is connected to the clock of the second flip-flop, and we are using the positive going edge of the clock pulse. Okay, now if we see the 2-bit triple down counter using the positive age triggered flip-flop. Okay, so a 2-bit triple down counter using the positive age triggered flip-flop you are observing here, and this is the timing diagram. Okay, now here Q1 output of the first flip-flop is connected to the clock of the second flip-flop. Okay, and the external clock signal, we can see it is applied to the first flip-flop. This first flip-flop will toggle at the positive going edge of each clock pulse, and this flip-flop 2 will toggle when this Q1 will change from 0 to 1, because it needs a positive pulse at the clock, right? Then only it will toggle. And these counting sequences, obviously it is since a down counter 001110 010011, like that. Okay, now we will see the 2-bit triple up down counter using the positive age triggered flip-flop. So here when M equals to 1, this up down counter using the negative age triggered flip-flop we have seen previously. So when this M is 1, what happens? This M is 1 for up counting. Okay, M is 1 for up counting, and Q1, what we can see is This Q1 bar, it is transmitted to the clock of the second flip-flop, and when M is 0, what happens? It is for down counting, and Q1 is transmitted to the clock of the second flip-flop, and this is achieved by 2 AND gates and 1 OR gate. So what will be the clock signal to my second flip-flop? It is Q1 bar into up counter, that means Q1 bar into M plus Q1 into down means M bar. Okay, so Q1 bar M plus Q1 M bar.